All right, hello everybody, welcome to video 12. In this video, we're going to be verifying trigonometric identities. Now here's something I'm going to start doing in particular with mod 6. In each of the videos, I'm going to try to outline a little bit better in terms of what is the goal in this lesson, goals if there's plural, and also kind of give you some direction in terms of where does this apply, where is this going to be used, if it's later in this class or if it's going to be more of a pre-cal, aka something you would see more in a second calculus class. Or excuse me, in a calculus class after this one. So your next math class. All right, and so in particular, this lesson, the goal is to essentially practice simplifying expressions. Through this, we're going to use what we learned in the previous video a ton. So again, if you have not watched video 11, make sure you go back and watch video 11. And then the second goal is to practice proving techniques. So in other words, practice proofs, because that's essentially what we're doing through verifying the identities. Where does this apply? So again, this applies in calculus, so simplifying what's called integrals, simplifying certain expressions so then I can actually work with it. And by going through and simplifying, we're essentially verifying and proving that this is equal to this, which is then equal to this, meaning that I can continue and work through the problem. The second is essentially in the next section, we're going to build up on this verifying trigonometric identities to verifying that certain formulas are accurate and going through and proving that and flowing through using these ideas. All right, so before we begin, and as we begin, what it means to verify it, it means to show that your equation is true. All right, so recall that an identity is an equation that is true no matter what your angle is, right? So as long as you can plug in your angle, the left-hand side will always be equal to the right-hand side. And so in some situations, one of those two sides may be easier to plug into and may be easier to use. And so this is why identities are so important, is because they establish some other relationships, better ways to maybe work through a problem than as originally written. For now, though, what we need to just do is make sure that we can even use these identities and that I'm not essentially lying to you when I say, for example, in example 1 here, that cosecant minus sine is always going to be equal to cosine times cotangent. All right. Now I want to go through, and I want you to, and I'm going to work this one through with you together. We want to go through and verify showing that this is true. In other words, that this left-hand side is equal to the right-hand side for all x that I'm allowed to plug in here. And so when I want to go through and I want to verify something, the very first step, which you'll see here on the left-hand side of the screen, is to go through and choose the hardest or most complex side of the equation. Now, and this is really due in part because of the second step, which is then to simplify, aka video 11, and the techniques learned in video 11. All right, and so when I'm going through in my first step here, when I want to choose the hardest looking side, what I'm going to do in every single problem is essentially go through and break up this problem into two sides along the equal sign here. So I have a left-hand side and I have a right-hand side. And I want to choose the hardest or most complex looking side because when you are simplifying, by choosing the hardest looking side, then that means you're going to have more to actually do and more to actually work with. It'll lead you a little bit longer in terms of your next step, versus if you were to choose the easiest side, you may have one thing that you can simplify, but then that might be it. So it sounds a little non-intuitive to go through and choose the hardest side, but when you actually start thinking about the logic behind it, it actually makes a little bit more sense to do that. And so in this problem here, I'm actually going to choose the left-hand side and work with this side because I know that I can go through and simplify cosecant and rewrite it, but then I can also combine this into one fraction. And then my goal is to get the right-hand side here. And so a lot of times when I tell people about verifying, essentially once you pick a side to work with, the other side becomes your solution. And then we're essentially working a video 11 type problem. I'm really just going through and wanting to simplify cosecant x minus sine x as much as possible, but I know that my goal is to get down into this. I'm looking for a cosine times cotangent. All right, and so the very first step that I'm going to do here is now simplifying. So I'm going to rewrite cosecant in terms of sine and cosine, in this case sine. And so I'm going to rewrite it as 1 over sine x. And then looking at this, I know that the second term here is over 1. And I want to write that because remember in our simplifying steps, once everything's written in terms of sine and cosine, I now want to move on into my step 3, which was to now use algebra. So I want to do PEMDAS. So that means I need to combine this into one fraction. All right, so I need a common denominator. So that means I'm going to rewrite the second fraction here so that it's over sine of x. Well, that means I have to multiply top and bottom by sine x. So up top would be sine squared. And then now I can make this one unified fraction by saying 1 minus sine squared up top all over that common denominator, which is a single sine. And then now thinking about through my simplifying steps again, step 1 says if you see a power of 2, you want to think Pythagorean. So I have 1 minus sine squared. Well, according to Pythagorean, that is cosine squared. This is all over sine. And so now I'm here. All right, now this is where I'm at so far in terms of simplifying. There's not much else I can really do with this. There's a couple different routes to rewrite, but I want to rewrite it specifically because again, I know what I'm looking for, right? I want a cosine out front. Well, if you look at the numerator here, I have 2 cosines in the numerator. So what if we pulled one cosine out? And this would be the cosine that's actually in front on the right-hand side. So then that would leave me cosine over sine in terms of the fraction. Well, cosine over sine is cotangent, and I now have verified this. In other words, that cosecant minus sine x is equal to cosine x cotangent x. And so this overall idea, this overall process that we just went through is this lesson. All right, that is what it means to verify. Now, the steps involved, there's multiple ways to look at this problem. There's multiple ways to simplify. So as I'm going through, if you look at the problem and say, well, I would have done this, then I would encourage you to continue that thought to see if you could still get it down and show that the left-hand side is the right-hand side or vice versa. Because again, there are different ways to simplify and different ways to apply the theorems. I'll try to, at the very beginning of each of the earlier examples, trying to point out the different routes you can take. I'm going to always try to take the most efficient one because I'm lazy. I'm a mathematician, and that's kind of the idea. But again, you can take a least efficient route if that's the route that you choose to take. All right, and so just be aware of that. Now there's also, if you'll notice, I did not fill out the step 3 to verifying. I will fill this out when we need to. There's really only some particular problems where step 3 will come in, and so I'm going to save that for now. The main steps of verifying are choose the hardest and most complex side, so either choose the left-hand side or the right-hand side. And then the second step is to simplify according to what we did in video 11 and the steps that went along with that. All right, so let's take a look at example 2. So example 2 is going to really kind of focus more on recognizing some Pythagorean identities first. So if you recall in example 1, we had the Pythagorean identity come in, but it was kind of throughout the problem as we were working it. In this example, I'm actually going to use the Pythagorean's identities early, and in terms of rearranging those original identities, because it can make my simplifying process easier than trying to apply them later. All right, so in this problem in part A, I have secant square root of x times 1 minus cosine squared x is equal to tangent x. Now, in terms of my simplifying steps, again, step 1 would say use Pythagorean. Step 2 would say change everything to sine and cosine. And so if you were looking at this, first off, I need to pick which side I want to work with. Well, intuitively and hopefully trivially, the left-hand side is the most complex looking side. So I want to simplify the left-hand side. Well, if I was to go through and rewrite everything in terms of sine and cosine and then distribute, I would have a little bit more work on my hands. Instead, what I'm going to do is I'm going to look at this 1 minus cosine squared, and we talked about in video 11 how this is sine squared, and that comes from, again, the first step of the first Pythagorean identity. If I was to solve for sine squared, that's the rearrangement that this problem is referring to. And so I actually have, then in brackets, this gets simplified down a little bit easier. the secant squared x I'll bring down here. Now the next step is actually to rewrite now secant in terms of cosine. So I can write this as cosine squared. And now when I multiply these two things together, I get sine squared over cosine squared, which is sine over cosine squared. Right? If you have a real power here, this power distributes between top and bottom in terms of the fraction. And so that means sine x over cosine x simplifies down to tangent squared. And I'm done because that is tangent squared of x. And we're finished. Again, by choosing the left-hand side, the right-hand side becomes my goal, becomes my solution. The second that we get down to an idea like this, we have verified and we have shown that it is true. Essentially, by going to here, we have completed the process. The next step was kind of a trivial step to take. Now, when you're going through and working problems like this, if you're tutoring or if you're grading me, you just want to make sure that you can follow the individual pieces. Give me as many steps as necessary to prove your point. If it's a tutoring assessment, I will be able to kind of ask some clarifying questions. How did you go from here to here? If you're doing an assessment and you're grading my work, you need to have that mindset of where did I go from this step to this step. And if it's not clear, you need to go through and make that correction or make that justification as to why you need to see that step. All right, so let's take a look at B now. Again, the idea here is to hopefully apply Pythagorean fairly early. Now, in this problem, there isn't anything squared except on the right-hand side, but the right-hand side is the easier looking side. So when I go through and I'm going to pick the hardest side again, I'm going to choose the left-hand side. There's no Pythagorean to work with here. So what I'm going to do is instead of rewriting secant as 1 over cosine, I'm going to go ahead and distribute this cosine of A out front here because I know that cosine and secant are multiplicative inverses. We talked about this idea again in video 11. And that cosine times secant is just going to give me 1 minus cosine times cosine or cosine squared. All right, and this is where again and why I talked about that idea and why it's so important. This again, hopefully you're just hearing me over and over as I say video 11, video 11, video 11. I told you in that video that it was very foundational to the section, and hopefully you're kind of seeing that and you're getting annoyed by me continuously saying that. Now 1 minus cosine squared, we have shown that this is just the rearrangement of sine squared in the Pythagorean. This is enough justification. The next step would literally be to just say that this right here is sine squared, and I would have sine squared is equal to sine squared, and so we're done at this stage. We have the solutions. So this is really just a one-step problem if you distribute the cosine instead of going through and rewriting it and then working inside the parentheses as you simplify. All right, so part C. This step, again, looking at it, the left-hand side is clearly going to be the most complex side. I mean, the right-hand side is just a 1. So obviously, that's the easier side. All right, and so looking at the left-hand side here, there's nothing squared in terms of simplifying, so I can't use Pythagorean right now. I could write everything in terms of sine and cosine, or I could just go ahead and simplify by doing some algebra. Now, I'm going to go ahead and choose to simplify just using algebra, and the reason why I'm going to choose to do that is because I noticed that I have a cosecant times a cotangent, and a cosecant and a cotangent. In other words, there's the same terms, but notice what's the only thing that's different between them. So this is essentially an a minus b times an a plus b scenario. It's a difference of squares. So just by looking at the overview of the problem, then instead of rewriting it and adding more trig expressions into this function, making it harder to look at, I'm going to go ahead and distribute and multiply this thing out. All right, and so I'm going to multiply or essentially FOIL. Now I know that when I do a minus b times a plus b types, that this is just a squared minus b squared. So it's cosine times cosecant times cosecant, or my a squared there, which is cosecant squared, and then minus b times b, which is cotangent times cotangent. And so I get this expression here, the cosecant squared x minus cotangent squared x. And this is why, again, that I'm choosing just to multiply this out instead of rewriting in terms of sine and cosine first. Because now when I do this, I have items that are squared, which are implying to use the Pythagorean identities. Now I see a cosecant and I see a cotangent. So that Pythagorean identity, it is the third one. And what it says is it says 1 plus cotangent squared of x is equal to cosecant squared. So I have a direct substitution for any cosecant squared that I see in the problem. So I'm going to make that substitution here for cosecant squared, that this is 1 plus cotangent squared. I'm going to drop down my minus cotangent squared, and we see that the cotangents will cancel. I will be left with 1, and we now have fully verified. And so this is why, again, that I don't want to change cosecant to 1 over sine or cotangent to cosine over sine, because by going ahead and distributing now and then applying my Pythagorean identity, I can actually verify in a much shorter process than I would, again, if I was to rewrite it. Now, as an exercise, and if it's something that you would like to try and do, I would encourage you to go through, like, what if you did change this problem and you rewrote it to be 1 over sine x minus cosine over x, or excuse me, cosine over sine, times 1 over sine plus cosine over sine. So in other words, what if you rewrote everything in terms of sine and cosine, like we talked about when we simplified? What would you do next, etc.? And you should, again, get down to an answer that's just 1, but you'll find that it's going to take multiple steps compared to the 2 steps it took here to get to the same result. So I would encourage you to continue that if you would like to, just to prove my point, or essentially just see how it works out. But I'll leave that as an exercise for you. All right, and that's the end of example 2. Now example 3, this is actually the final example, and this is really going to be looking at problems from A to, I think, H. So that's roughly A, B, C, D, E, F, G, H, so like 8 different types of verifying problems to see. So as we're going through and working through these problems, feel free to skip to different types of examples. They will increase in terms of difficulty. And so if you want to look at some more harder ones, skip ahead to like something like letter, G and H. If you want to start with the easier ones and progress through, do that. Let me work the first one, you try the next one. Whatever you would like to do, whatever your learning process is, choose to do that. That again is the great thing about this video. So take advantage of that availability and that option. So example 3, the directions are just going to say to verify or to verify each of the following trig identities. Verify, again, just means to show that it is true, and we're going to go through and work through our verifying steps. The first step to verifying is to, again, in part A here, I'm going to choose the most complex looking side. For me, I'm always going to choose when I'm adding and subtracting. So I'm going to pick the left-hand side here, and I want to simplify it and get it down to cosecant times secant. That's my goal. All right, so tangent, I know I can rewrite it. Tangent is sine over cosine. Plus cotangent is cosine over sine. And I need to now simplify. So I need to add things that I can add, subtract things I can subtract. Well, I'm looking at doing work with fractions. So I need to find a common denominator. Well, that common denominator is going to be both denominators together. So that's going to be sine times cosine. Now, make sure that you're putting these x's here, that you're not just writing sine cosine. This expression here is not the same thing as sine of x cosine of x. Remember that these are functions, and they are functions of x, so we have to specify that. Otherwise, when you write it like on the left-hand side here, it looks like you're saying sine of cosine, which could be a thing, and we don't want to look at it that way. So just be really, really careful as you write that. Make sure to include your variables. Don't get lazy on me as you're going through and doing this work. All right, so going back to the problem here. So we have our common denominator as sine x cosine x. So that means for the first fraction, I needed to multiply top and bottom by an extra sign. So that's going to give me sine squared. For the second fraction, I needed to multiply top and bottom by a cosine. So that would give me a cosine squared. Making this one unified fraction, I would get sine squared plus cosine squared. Wink, wink. all over sine times cosine on the bottom. Now, sine squared plus cosine squared is a Pythagorean identity. I told you as we looked at that you need to memorize this one. That is always going to be equal to 1. And so now I have this. Now, you may look at this and say, okay, now what else am I supposed to do here? All right, and this is where I'll go ahead and institute the step 3 in terms of how do we verify. When we verify, if you get stuck in working with one side, move to the other side. In other words, start simplifying the other side as much as you can, because then maybe you can simplify it either down to the form you already have on the left-hand side, or you can simplify it a little bit more so you can see what you're supposed to do on the left-hand side, like what that next step may be. So it's kind of a reverse engineering type problem, or as Michael Scott would say, reverse psychology. All right, so what I'm going to do is I'm going to turn to this cosecant x secant x, and in terms of simplifying, that means I would rewrite it as 1 over sine times 1 over cosine. And if you notice, that's exactly where we're at with the left-hand side here, 1 over sine x cosine x, because once I multiply these two things together, that's exactly what I would get. So on the left-hand side, if I did not want to work with the right, the next step would be to literally break this down into 1 over sine times 1 over cosine, and then we have the verification like we just talked about. So we were actually pretty much done once we got here. But step 3 again, and I'm going to fill this in at the top, is to work with the other side. That's the next step. All right, so that was A. All right, so let's take a look at B. So sine x plus sine x cotangent squared x is equal to cosecant. All right, I need to verify, so I'm going to pick the harder looking side. In this case, again, I'm going to choose the left-hand side. I'm going to continue writing in blue, so that way it'll be a little bit easier to see which part is the solutions and which part is the work. I'll change the color in part A's work after this. So when I post it, it'll be a little bit easier to see. Okay, so in this problem, I want to show you a technique that we can actually do. This is something we've worked on a little bit beforehand, but it's just going to make our lives a little bit easier. And what that technique is notice that in both of these two terms here, I have a sine x in common, and specifically a single sine x in common. So I'm going to factor that one sine x out. And if I do that, that means out of this term, I would be left with a 1, plus here, I would be left with cotangent squared. And if you're asking, like, why would I do that versus changing cotangent squared to, cosine over sine, the reason is because look at what's in brackets. This is a Pythagorean identity. So what example 2 had shown us was that if I can use this early, it'll make my life a lot easier. So by noticing that both of these terms have a sign, and by taking that sign out would leave me with this result, I'm going to take that result every single time if I can. So this in parentheses, the 1 or in brackets, this 1 plus cotangent squared. We have looked at this before. I actually have it up, I think, in example 2, that this is directly equal to cosecant squared. So that's what's here in brackets. Again, sine and cosecant are multiplicative inverses. So I know that when I multiply sine and I multiply a cosecant, that's going to give me 1. So notice I have 2 cosecants here. So this is really this if I was to expand it all. And this piece right here, again, is equal to 1. So that would leave me with 1 times cosecant, or just cosecant of x. And I verified, I'm done. All right, part C. And I'm going to give myself a little bit more space here. Move this down just a little bit. All right, so sine x minus cosecant x all over cosecant is equal to negative cosine squared. All right, so again, I'm going to choose the left-hand side. I'm going to choose this side because it is the more complex side. Notice that most of the time the left-hand side is that, but you don't have to just assume. Make sure you're looking at it and choosing through it all. All right, so sine x minus cosine x all over cosecant x all over cosecant x. I'm going to go through and I'm going to rewrite. So sine of x minus, so cosecant again is 1 over sine. This is all over. 1 over sine. All right, so I need to go through and do algebra. So I'm dividing by a fraction. So what I'm really doing is multiplying by its reciprocal. So I have my numerator, which is sine of x minus 1 over sine of x. And I'm now multiplying, so changing it, and flipping. So this would be sine x over 1, or just sine of x. So I'm just going to leave it as just sine x here. And so now I'm going to take this sine x and I'm going to distribute it throughout my parentheses, throughout this grouping here. So doing the first one on the left, so sine x times sine x is sine squared, minus 1 over sine x times sine x is just 1. In other words, 1 over sine x is cosecant. Cosecant times sine, they're multiplicative inverses. Thus, I'm going to get just the minus 1 there. All right, now notice how this is very, very similar to the Pythagorean being rearranged. And so I kind of want you to, I don't know, I'm trying to think of exactly how to show you this. I guess one of the easiest is when we did sine squared plus cosine squared and set this equal to 1. If I was to solve for cosine squared, because that's pretty close to what this is, this would be my rearrangement. Now, notice how on the left-hand side right here, this is backwards from what we have in the identity. And notice that what I'm trying to get is also backwards in the sense of it's negative. So if you were to negate this identity, negative cosine squared, and then over here you get a minus 1 plus sine squared, we actually show that this is equal to negative cosine squared, because this right here is sine squared minus 1. So this is just one approach to kind of showing it. The other approach is to actually solve for sine squared out of the Pythagorean, so do that rearrangement, and then make that substitution here for sine squared, and then simplify. That I think is the other easy way to kind of see the work done, but it is enough just justification here that those two things are equal. Okay, so part D. So 1 plus cosecant of x divided by cotangent x plus cosine x is equal to secant x. So notice we're starting to get into a lot of fraction work. So a lot of the times when we have this fraction work, the process is very, very, very similar. Again, I'm going to choose this left-hand side here. All right, and I have 1 plus cosecant of x over cotangent of x plus cosine x. All right, and so I'm going to go through and rewrite everything in terms of sine and cosine. So I have 1 plus cosecant is 1 over sine. All right, cotangent is cosine over sine. And then plus cosine. All right, now, depending on who you have as a teacher, there are different ways to go through and work this. This is called a complex fraction. Again, I have fractions within a fraction. Now, for me, what I told you beforehand, and we did this in terms of video 11, is when I look at an expression like this, I'm going to multiply top and bottom by the common denominator between all of my fractions. So when I look at each individual piece here, so here, 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 and here, notice that there's really only one denominator, which is sine of x. So I'm going to multiply top and bottom by sine of x here. Now notice by multiplying top and bottom, this is really just 1, so I'm not changing the overall problem. This is just a manipulation technique. Now this sine x though has to distribute to everything in the top and the bottom. So when I go through and multiply this out, we would get sine of x times 1, which is just sine of x, and then sine of x times 1 over sine, which would be plus 1, because those two things would cancel. This would be all over. Sine of x times cosine over sine, which is cosine x, sines would cancel, plus here cosine sine. If you're looking at the denominator, and we've seen something like this before, see how now I have a cosine here and a cosine here, and by bringing that single cosine out, it will allow me to simplify, because the denominator would then be cosine of x and then remaining 1 plus sine x, which is the exact same expression, just with the order flip-flopped, but because it's plus, it doesn't matter. That these two expressions are exactly the same, meaning I can cancel them out. So this would boil down to a 1 over cosine of x. It's still in the denominator, which as a reciprocal identity is secant. And we have now verified. All right, taking a look at E. So again, I'm going to move F down just a little bit. And I thought we were going down to H, but we may actually just go down to, oh, nope, we are going to H. All right, so doing E. All right, again, I'm going to look at both sides here. So I'm going to separate this. The hardest looking side to me is the left-hand side here. So I'm going to work with just this side. Now, when I go through and look at this type of problem, again, I'm going to rewrite everything. That's just the approach that I'm going to take here. So I'm going to rewrite, so cosecant is 1 over sine, minus secant is 1 over cosine. This is all over. Cosecant, which is 1 over sine, times secant, which is 1 over cosine. So now my denominator is just really, and I just want to rewrite it this way, so that way the next step is clear. So the numerator, again, I'm just going to keep the same for now. The denominator is 1 over sine x cosine x. Because multiplication, top times top, bottom times bottom. Now notice that, again, I'm dividing by a fraction. So I'm going to rewrite this. So I've got the numerator, which is 1 over sine, minus 1 over cosine. And I'm multiplying this by the flip of the denominator. So flipping that would just give me sine x cosine x. This is why I'm taking this approach. Because now when I take this sine x cosine x and I distribute it to the pieces that are in the bracket, this first time that I multiply it out, the sine x and the sine x on the bottom will cancel. I will be left with just cosine of x. Minus, when I do the second fraction here, the cosines will now cancel, and I'll be left with just a sine x. And there's my final, because again, if you look at the right-hand side, that's what I was trying to get. We're now verified. Let's take a look at F. Cosecant of x plus cotangent x is equal to 1 over cosecant x minus cotangent x. Now this one, if I was to separate, I think is where the argument that essentially the left-hand side or the right-hand side could be the easiest to work with. I'm going to go through and show you using the right-hand side. So let's swap it up a little bit. Now in your practice for simplifying trigonometric expressions, it is question number 1 that I think talks about this, that if you have something 1 over and I have a fraction, what I can actually do is multiply top and bottom by its conjugate. So in other words, I can multiply top and bottom by cosecant of x plus cotangent x. And if I'm going to multiply the bottom, I need to multiply the top. And again, this is called multiplying by the conjugate. The conjugate, again, is just referring to changing the sign. So if originally I have a minus here, I'm going to multiply top and bottom by a plus. Now, these two things, again, are the same expression. So all I'm doing is manipulating the work. I'm not changing it. That's why I'm not multiplying the other side. And so I'm just going to multiply this out. So I'm going to have up top, I keep writing CC, CSC, so cosecant x plus cotangent x. And now when I multiply out the bottom, I want you to notice that because it's conjugates, this is the a minus b times a plus b. It's that difference of squares again. So the denominator is just going to be the first terms multiplied together, so cosecant squared, minus the bottoms multiplied together, the b's, the second pieces multiplied together. So I get cosecant squared minus cotangent squared. Well, if I'm looking at the numerator is my solution, right? I get cosecant x plus cotangent x, and that's what I'm supposed to have. So what that's telling me in terms of context is I need to be able to get rid of this somehow, or this simplifies away. So notice that both terms here are squared, so I could use my Pythagorean, and according to the third Pythagorean identity, I know that 1 plus cotangent squared is equal to cosecant squared. And we've done this one before, I think even above in a different example, by substituting 1 plus cotangent squared in for cosecant. A cotangent squareds cancel, and I'm left with just cosecant of x plus cotangent of x over 1. which is cosecant of x plus cotangent of x. I'm done. All right, again, refer to the earlier example. We've done that simplification, specifically that cosecant squared of x minus cotangent of x is equal to 1, if you want to see that intermediate step. All right, so taking a look at G, there's H, so we're almost done. Let's get this down just a little bit. All right, so here's G. 1 minus cosine of x over sine x is equal to sine x over 1 plus cosine of x. Again, this is a problem where looking at the left and right hand side here, they're both about equally as hard. I'm going to choose the right hand side. Just like before, it's mostly because the denominator contains the 1 plus cosine of x. And when I multiply here, I'm going to choose to use that conjugate idea. So I'm going to multiply by 1 minus cosine x on the bottom, and then I have to do 1 minus cosine x up top. So again, what's determining that is this 1 plus cosine of x. I'm changing the sign here in the middle. And if I'm multiplying the bottom by that, I need to multiply the top as well. Notice that by doing the conjugate idea, that's giving me the numerator here that I have on the left-hand side of what I want. So I know that this multiplication is going in the right track because I'm starting to see pieces that I should get in my final answer in terms of my work here. Now, the top is just sine of x times 1 minus cosine. I don't want to distribute that again because I'm supposed to get 1 minus cosine. On the denominator, again, I'm multiplying the conjugates. It's a difference of squares. So 1 times 1 is 1, minus cosine times cosine is cosine squared. And 1 minus cosine squared is a Pythagorean. Specifically, it is equal to sine squared. So I'm going to make that substitution. So at the top, I'm just rewritten. On the bottom, I have a sine squared. And this is where one sine will cancel out with one sine here. And I get my final 1 minus cosine x over sine of x. Verified. All right, so again, these two problems incorporate this idea here of using the conjugate. All right, now H. All right, so this is our final, and then we'll do our closure. I'm going to move this down. So I just have a little bit of space, and then we'll talk about we'll talk about this in a minute. So last example here, so H. I have 1 minus 2 cosine squared over sine x cosine of x is equal to tangent x minus cotangent x. Okay, this is going to be a little tricky, but I think we can figure it out. Okay, so I'm going to work with the left-hand side here because I want to show you an idea. And it centers on this idea that I can't change anything in terms of sine and cosine. Now, I could go through and I could replace cosine squared with Pythagorean, but instead, what I'm actually going to replace here is the 1. So I know, according to Pythagorean, that sine squared plus cosine squared is equal to 1. And that's the substitution I'm going to make. I'm going to plug this in to the 1 here I have highlighted in red. So that way that my numerator becomes sine squared plus cosine squared minus 2 cosine squared. And this is all over sine of x, cosine of x. Now, I'm really just kind of showing you this approach. It's kind of one that a lot of people might not see, but it's something that you're allowed to do. You don't have to substitute just for a trig and using Pythagorean. You can replace any number 1 with this because 1 is equal to, we have that equivalency. So I'm making that substitution. Now, when I do that substitution, I can simplify my cosine squareds here. I've got 1 cosine squared minus 2. So this would give me sine squared minus cosine squared in the numerator. This is all over my sine x of cosine x. And I did it specifically this way because, remember, I'm trying to get tangent of x minus cotangent. And now by splitting this up into 2 separate fractions, we will actually get the second to last step here. Now, by separating this out, I can write any individual term in the numerator as 2 fractions over that common denominator, like so. And by doing that, notice that I can get rid of 1 sine here, and I can get rid of 1 cosine here. So I have sine over cosine minus cosine over sine. And these pieces taken individually as quotient identities is tangent minus cotangent, and we're done. Okay, so in closure, these steps to verifying. 1, pick the hardest side. We need stuff to work with because the next step is to simplify. Now, when you are simplifying, steps to simplify. 1, go through, if you have anything squared, see if you can use any of your Pythagorean identities. So again, this is anytime you see a power of 2. Second step, rewrite in terms of sine and cosine. So and or cosine there. The third step when you're simplifying is to then just apply your algebra techniques, which is PEMDAS. Now, these 3 steps can be done in any order. You don't have to follow them 1, 2, 3. You may do algebra first, rewrite, and then use Pythagorean. It just depends on your problem and which steps that you see you need to take. But either of the cases, these are your steps to simplifying the things you need to look for. Now, in terms of verifying, after you have simplified, there may come a time where just working with one side does not work. You need to work with the other side. Now, these occasions can be kind of rare, but you could still do that. All right, so when we're verifying, your 3 steps again, pick the hardest looking side, simplify according to the previous video. Those steps are listed to the right. And then the third step is to work with the other side. Again, make it look like where you're at on the left-hand side or the right-hand side, what other side you started with. All right, and so that's it for this video. Make sure to take a look at the practice. You're going to have plenty of different types of equations to verify and to go through and work through these steps and processes as normal. Shoot me a message, either an email or a group me, and let me know how I can help you. These objectives, again, if you're watching this at the end of Mod 5, we will assess on simplifying and verifying in Mod 6. So you will see these objectives. And so this video is still very important. I want to make sure that you have an opportunity to master these techniques. All right, and that's it. Thank you for watching, and I look forward to hearing from you.